Hey everyone, welcome back, and today let's solve Leetcode problem 1277 titled Count Square Submatrices with All Ones. So pretty short problem statement here, pretty straightforward and concise. We're given an m by n matrix of ones and zeros, and we need to return how many square submatrices have all ones. Okay, so in example 1 we have the input to the array matrix to be the following, and we'd output 15. They also give us a nice detailed explanation of why that is. There's going to be 10 squares, obviously, with side 1, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 ones in our input array matrix. And there's 4 squares of side 2 and only 1 square with side 3. And so if you add all those different squares up, you get 10 plus 4 plus 1, which is going to give us a total return value or output of 15, which is why we output 15 for this test case, right? The reason why is this is going to be a square, right? This right here. This is also going to be a square. So is this, and so is this, right? So these 4 squares of side 2 are going to be the 4 squares that we also have to add. And this, we only have 1 square of side 3. It's going to be this big chunk right here of 9 ones. And so that's going to give us 10 plus 4 plus 1, which is 15 total squares. They don't have to be 1 by 1. It can be any square that's going to be symmetrical, or n by n. So in example 2, we have the input to the array matrix to be the following, and we'd output 7 because there's already 6 ones, right? And you know, each one can make its own square because we can't have squares with side 1, right? And we also have 1 squared of side 2 right here. It's going to be 1, 1, 1, 1, and so that would be 2, and so the total number of squares is going to be 6 plus 1, which is a return or output value of 7. Alright, so with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, sorry guys, I just realized I was talking a little bit too fast at the end there. I'll try to slow down how fast I talk so it's a little bit more understandable. Okay, so to solve this problem efficiently, we're going to be using dynamic programming, right? And we'll do this to build the solution by gradually expanding our understanding of the number of squares in the matrix. We'll start with smaller squares and expand to larger ones, right? So to kind of just explain how this DP solution is going to be structured, we'll have every single index ij in our DP array to store the size of the largest square that ends at the cell I, j. And if and only if the value at matrix ij is 1, we can only try to extend the square formed by its neighboring cells, which are the 4 directionally adjacent cells, left, right, and top, down. Right? And we'll also use a variable, I'm just going to call it total squares, and this is going to keep track of the total number of square submatrices that we're ultimately going to return after we're done with our algorithm. Right, so with that out of the way, let's just go ahead and dive straight into the code here. Right, so I'm going to initialize my m and n, like I always do in my matrix problems, to be equal to the length of my matrix, and the length of matrix at index 0. Okay, I realize I can't spell. Matrix at index 0, right? Where again, m and n are going to initialize to the number of rows and the number of columns in our input to the array matrix, respectively, right? And this is just for easy access when we actually want to iterate over the matrix. We, instead of just calling these two large variables, if you will, we can just simply access them using m and l. Right, once we do that, now we want to actually instantiate or initialize our 2D DP array. Right, so we'll set DP equal to an array of 0 times n for I, actually let's just use a underscore as my placeholder, for blank in the range of m. Okay, this is pretty Pythonic, it's a list comprehension here, but nothing too crazy. We're simply initializing this 2D list, and it's going to be having m rows and n columns. Its dimensions are going to be m by n, the same of which our input array matrix is for every single test case, right? Where each cell, obviously, in this DP table is going to be initialized to 0. And again, DP at index I, index j, is going to store the size of the largest square ending at that cell, I, j, right? So we're going to have dimensions, again, n by n for this DP array. And every single cell in this 2D array that we actually define is going to have, or initialize to be 0. right? Once we do that, now we can actually initialize our total squares variable like we talked about before. This is going to be set to 0, and it's ultimately going to store the total number of square submatrices with all ones that we actually find as we traverse through this input array matrix. So now we can actually begin traversing through our input, and it's pretty simple. We just have to have nested loops to iterate through every single row and column to explore all the different cells. So I'm going to say as my outer loop for I in the range M. We'll note that again, that's going to store the number of rows we have in our input array matrix for every test case. And for, actually, I'll replace this with R and C. I think that's a little bit better. For C in the range of N, again, this is basically iterating through the current column, or C again is our iterator to represent column. And now we have to check if the matrix in this current iteration, if the matrix, at index R, okay, I really cannot spell today, sorry about that. If the matrix at index R, index C, if that's equal to a 1, again, if it's a 1, only then can we actually proceed to determine how large of a square we can actually end at position ij. Because again, we know that we only want to return squares that have all 1s. And so only if it's a 1, we can actually try to determine how big our square is that ends at this position, m comma n. Right, I know I've been saying ij. I wanted to do ij, but because that's the nested or standard iterators for loops, but I'm going to say rc, so it's a little bit more understandable for row and column. Okay, so if the matrix at index r and at index c is actually equal to a 1, now we have to have another base case. If the current row is equal to 0, or the current column, c, is also equal to 0, and this basically checks if the current cell is on the top row or leftmost column, we can only form a 1 by 1 square, right? And that's because there's no cells above or to the left to actually form a larger square. And so if that's the case, we want to set, pretty self-explanatory, GP at index R at index C to be initialized to 1, right? Because for top row or left column cells that contain a 1, we have to set dp at that index ij to be 1, since they can only store or form 1 by 1 squares, right? And then we're going to have our else conditional when we don't have a square that kind of goes out of bounds with its neighboring cells. If that's the case, we want to set dp at ij, dp at index I, index j, and this is the main part or our core of our dp code. It's going to be equal to the minimum of, watch this, dp at index I minus 1j. Actually, I'll format this a little bit better. I'll say ij minus 1, ij minus 1, or actually, yeah, it doesn't really matter. Ij minus 1 is going to be the minimum of dp at I minus 1j. And for our final value, it's going to be dp at I minus 1 and j minus 1. And finally, we have to, of course, add a 1 to that minimum value, so plus 1. Why is that? Okay, so this basically says, and this else conditional checks for other cells that aren't on the edge, we also have to determine how large of a square can actually be formed at that index ij, or at that cell value. And we have to take the minimum of the 3 neighboring cells, which is going to be dp at I minus 1j, as you guys see right here. That's going to be the top cell. We have to also take the minimum of dp at ij minus 1, which is going to be the left cell, and we have to take the minimum of dp at I minus 1j minus 1, which is going to be the top left diagonal cell. And we have to add 1 to this minimum value to actually extend the square size at that index I comma j by 1. Okay, and once we do that, we want to increment total squares by dp at index I, index j. Right? Pretty self-explanatory here. We have to simply add the value at that cell in the dp2d array to the total squares variable. And that means we're actually counting all the squares ending at this position, I comma j, and ultimately outside of this nested loop, once we're done traversing through every cell in our input 2D array matrix, we can return the number of total squares that we actually found consisting of only 1s, because it will have stored or given us the result of the total number of square submatrices that actually have only ones in the input array matrix. So as you can see, if I were to submit this right now, unless I made any syntax errors here, this should be accepted. Okay, let's see what I did wrong here. Okay, sorry about that. I accidentally used I and J again. Completely crossed my mind that we switched our iterators. Sorry about that. It's going to be R and C. Feel free to just fast forward this part. This is just me refactoring or debugging my code because I forgot that we're changing our iterators. I'm going to set this to be R and C. Okay. So now this should work. I probably didn't spell anything wrong apart from those things. This should be accepted. And as you can see, this is just about as efficient as you can get. Okay, so what does this code do overall? Okay, to better explain what this code does overall, we simply have to use these nested loops to scan through or traverse through the input matrix cell by cell. And if a cell contains a 1, we need to calculate the size of the largest square submatrix that ends at that position using the values from the neighboring cells. And it keeps track of the total count of all such squares using that total squares variable. And this DP table that we made is going to help us build this solution incrementally so that larger squares are actually counted by building on smaller ones accurately. Right? So for the time complexity of this code, this is going to iterate through each element of the matrix exactly once. And we use a nested loop for this. And so the time complexity of this code is going to be big O of m times n, where again, m is going to be the number of rows and n is the number of columns. And for the space complexity, we do use a extra 2D DP table of size m by n. And so the space complexity is also going to be big O of m by n, where again, m and n are the rows and columns in our input matrix respectively. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.